Welcome to the second part of the 8th lecture on earthquake resistant design of structures. In the previous lecture, we were discussing about an example which was showing us how to design a beam for earthquake resistance, and this was taking into account the IS 13920, which is the ductile detailing code for earthquake resistant design of structures, as well as IS 456, which is the Indian standard code for the reinforced concrete design of structures. So let us go with the brief overview of what we discussed in the earlier lecture. We discussed about an explanatory example which was meant to show us how the ductile detailing is provided in the beams for RC structures. Now in this RC frame which was taken, which was a 4-story frame with 3 number of bays in X direction and 2 number of bays in the Y direction, we began analyzing it. The lateral load distribution was obtained as in the earlier lectures. Thereafter, the analysis of this was done for these lateral loads in X and Y direction. The parameters of the beam structure were given to us. Finally, the load combinations were also available to us. Thereafter, the load analysis was done for a beam AB, BC and CD. Now this beam was located somewhere here in the 3rd story of the building, and the load analysis was provided. Now the structure after analysis had these reactions and these moments, and these as the shear forces. Now moving ahead in this lecture, what we will be discussing is that we would be designing the beam. Now what is available to us is that this is our structure which has got the beam AB, BC and CD, which is located at this location. Now this beam design involves the first step, which is that we check the beam for various things. The first thing is the check for axial stresses. Now no axial stress was considered to be acting here on this beam. Thereby the factored axial stress was 0, and this should be as per clause 6.1.1 of IS 13920, it should be less than 0.1 FCK. Hence we had to design this member as a flexural member. Next, what we have to check is the member size. Now if this beam BC, which we are talking about, if we provide it as 300 mm width and 600 mm depth, and then the beam width should be greater than 200 mm, as we saw in the clause 6.1.3 in IS 13920, so that clause is met. Next, the depth of the beam is 600 mm. Now there is a clause 6.1.2 which states that B by D ratio, that's the breadth to the depth, overall depth ratio, should be greater than 0.3. Now here it's provided as 0.1, so again this clause is also met. The third clause, which is provided by 6.1.4 in IS 13920, is that the length of the beam to the depth of the beam should be 8.33, should be greater than 4. Now here the length is 5000 mm and the depth is 600 mm, so it's 8.33. Hence again it's okay. Now these all checks are made for member sizes for ductility purposes. The third check that is provided is for limiting longitudinal reinforcement. Now what is the longitudinal reinforcement that we provide in the beam? It's the tension bars that are running at the bottom and the compression bars or the anchor bars which are running at the top. Now the effective depth for moderate exposure conditions with 20 mm diameter bars in 2 layers on an average would be, let's look at the what we have. This is the beam, and if the total depth is 600 mm, then the effective depth, if the reinforcement is provided in 2 rows, it would be 600 minus 30 is the cover, then minus 8, it's the distance between the 2 bars, again 20, it's the distance, is the dia of the first bar, then minus 20 by 2, it's half the dia of the second bar, thereby it's 532. Now, having known this D, which is 532 mm, the minimum reinforcement which has to be provided as per clause 6.2.1b of IS 13920, the Indian Standard Code, the minimum reinforcement has to be 0.24 into under root of FCK by Fy. Now 0.24 into under root of 20 here, where we know it's M20 grade concrete and Fy is 415. So the minimum reinforcement that needs to be provided is 0.26%, and 0.26 into 300 into 532 divided by 100. Now that would be 415 mm square. The maximum reinforcement that we provide is 2.5% as per clause 6.2.2. Now these criterias that are fixed for minimum and maximum reinforcement are again based on the ductility properties of the structural element, and it's also based on other factors like the shear reinforcement that is to be needed in the structural elements. Further, the reinforcement spacing, the amount of spacing between the reinforcement is also a criteria which decides the minimum reinforcement that is to be provided. Now the maximum reinforcement, which is 2.5%, is 2.5 of 300 into 532 by 100, that would be 3990 here. Here 300 is the breadth and 532 is the depth. It's B into D, small d. Next, what we know is that now we have to design this beam for flexure of beam BC. Now here we had to design it for hogging and sagging moments. Now this is the beam that we know, this is BC. Here the moment is 139.412, here the moment is 182.86, and at the center somewhere there might be some amount of moment, and there may be a counterflexure point at some other point. Now what is the moment, the overall moment, the maximum moment? It's mu. The factored moment is 1.5 times 182.86, it's 274.29. Thereby mu by bd square would be 274.29 into 10 raised power 6 in Newton mm divided by 300 mm, which d, 532, which d into 532, which d, it's b d square, and so it's equal to 3.23. Now we refer to table 50 of SP16. Now this is table 50 of SP16 for FY 415 and FCK 20. What's given to us is that there are 4 values for d dash by d between 0.1 and 0.15. Here d dash by d is 0.13. Here d dash by d is 68 divided by 532, it's 0.13. What we get is that we have 4 values for mu by bd square. It's varying from 3.2 to 3.3, it's 3.23. So we take the average value between these 4 values. 1.091 is, it's here, 1.099, 1.122 and 1.131. I have taken a approximately average value interpolated here, and what we get is that AST at the top is 1.11% for this condition of mu by bd square from SP16. Thereby this would be equal to 1.11 into 300 into 532 by 100. That would mean reinforcement of 1771.56 mm square. So it would be greater than the minimum reinforcement that we require that's needed, which was minimum reinforcement was 415 square, maximum was 3990. It's less than 3990. Now ASC at the bottom is at least 50% of AST, hence we are simply providing 1.11 divided by 2, it's 0.56% as per clause 6.2.3. This is the condition, 50% of AST for ASC. So ASC at the bottom is 0.56 into 300 into 532 divided by 100, so it's 893.76 square. Thereby, now we have the AST as well as ASC values. Next, what we are going to do is that we are going to detail the reinforcement, the longitudinal reinforcement bars. This is the continuous beam BC that we know, that we are talking about. This is the beam BC we are talking about. It's a continuous beam. Thereby, the longitudinal bars will run through the columns to the next beam. Now, what I have done is that I have detailed it. I have provided 5 number of bars at the top, 20 mm, and 1 number of bars, 16 mm. What we require is a reinforcement of 1771.56 at the top and 893.76 at the bottom. So we are obtaining a reinforcement of 893.76 at the bottom and 1771.56 by providing such reinforcement at top and at bottom. Next, we move to the shear design of this beam. Now, the tensile steel that's provided at the ends is 1.11%. How? We know it from here. It's 1.11% AST at top. So the tensile steel that's provided is 1.11%. Thereby, the permissible design shear stress of concrete as per IS 456 table 19 is tau c is 0.645. It's the value between, for M20 grade, which is of which this example is given here, the so reinforcement amount is between 1 and 1.25. It's 1.11. Thereby, what we get the value of tau c is 0.645 Newton per mm square into BD. B is 300 into D, which is 532 divided by 1000. We obtain it in kilonewtons, 102.9 kilonewton. Similarly, design shear strength of concrete at center and right end is evaluated as 51.45 kilonewton and 102.9 kilonewton respectively. Thereby, because there is half reinforcement provided at the center. The shear force, there are certain shear forces which act in addition to the normal shear forces that are acting in the beam. Now these shear forces are acting due to the plastic hinge formation at the ends of the beam during lateral sway and deformations. The additional shear due to the formation of plastic hinge at both ends of the beam is evaluated as per clause 6.3.3 of IS 13920/1993 and is given by this. V sway is 1 plus minus 1.4 mu AS plus mu BH by L, and V sway to the left is plus minus 1.4 mu AH plus mu BS by L. The sagging and the hogging moments of resistance mu AS and mu BS, mu AH and mu BH at both ends of the beam are calculated on the basis of actual area of the steel provided in the section. The beam is further provided with a steel area of 1771 mm square that we saw earlier. The longitudinal steel that was provided was 1.11%, which was 1771 at top, and 893.76 mm square, which was 0.56% at the bottom on the left end of the beam. Now, where do we get this? We have for the steel area of 1.11% and compression area of 0.56. Referring to table 50 of SP16, again For PT 1.11% or PC 0.56%, whichever gives lowest value in the table, what we obtain is the MUAH by BD square ratio would be 3.3. Now, what is the purpose of V being a factor of the moments at the two ends? What's the reason? The reason is that at the two ends there are different moments when the sway is happening towards one end, and there are different moments when the sway is acting towards the other end, and it depends actually on the actual area of the steel that's provided, not on the area that's to be provided. So it's the actual real area that's of the steel that's provided. Thereby MUH is by BD square is 3.3. Thereby the hogging moment capacity at A and now this A end is actually the B end of beam BC, that you must remember. Now MUAH is equal to 3.3 into 300 into 532 square divided by 10 raised power 6, so it's 280.19. This comes from this formula, 3.3 into BD square. So the hogging moment capacity at end A is obtained from this process. Once we know this, for calculation of MUAS, now this is the sagging moment. The tensile steel PT that's given is 0.56 and the compression steel PC is 1.11% is used. The contribution of the compression steel is ignored while calculating the sagging moment capacity as T beam. Now we will refer to annexure G of IS 456. Sagging moment capacity at A for XU less than DF and XU less than XU max. It may be calculated if you refer back to IS 456 annexure G. This is the formula. MUAS is 0.87 Fy AST into D into 1 minus AST Fy by BF D FCK, which is equal to 0.87 into 415 into 1.11 into 300 into 532 into 532. If we convert this AST into, if we convert the percentage steel into AST into 1 minus, so what we get is the value of 261.9 kilonewton meter of MUAS. Similarly, MUBH would be 280.19 and MUBS would be 261.9. Thereby, what we need to do is that we need to design this beam for shear. So V sway towards the right is plus minus 1.4 MUAS plus MUBH by L. Now we know the value of MUAS is 261.9. We know the value of MUBH, it's 280.19. The value of L is 5 meters. Thereby we get this value 151.78. In the light to light terms, we get V sway towards the left equal to 151.78. Now the shear at the left end for sway towards the left, VUA sway towards the right is 1.2 dead load plus live load divided by 2 plus 1.4 MUAS plus MUBH by L. Now for this you need to refer to IS 13920 and you will get this formula VUA, and this is again in the same section for the beam design for shear. So what you get is 1.2. We know already the dead load plus live load is 11.2 and into 5, it being the amount of shear at the left end divided by 2. This is 11.2 kilonewton per meter. So we have converted into the total load on the beam, plus we already know this value of 1.4 MU. So this is the value we get for VUA sway towards the right. Shear at left hand for sway towards the right would be 1.2 dead load plus live load by 2 minus 1.4 MUAS. So we get this value. Similarly, the shear at the right end for sway towards the right would be VUB, and this would be the formula, and this is the value 185.38 that we get. Shear at right end for sway towards the left, VUB sway towards the left at the right end, that's the other end, that's the actually the C end of beam BC. It's 1.2 dead load plus live load divided by 2 minus 1.4 MUAS, M plus MUBH divided by L. So what we get is 118.13. Now, as per IS 13920 clause 6.3.3, the design shear force that's to be resisted shall be maximum of calculated factored shear forces as per analysis, or shear force due to the formation of plastic hinge at both ends of the beam plus factored gravity load on the span. Now, hence here there is either you have to take the value of calculated shear forces. Now we have calculated that already in the previous lecture. In the other part of the lecture, what we obtained is this value was 42.06 into 1.5 is factored, it's 63.09 at end B of the beam. At end C of the beam BC, it's 47.42 into 1.5, 71.13. So the larger one is 71.13 here. Thereby, hence the design shear force will be 185.38, because the maximum that's obtained from analysis, shear analysis, is 71.13, and what we obtained from the plastic hinge formation is this 185.38. So we had to take the greater of the two. The greater of 185.38 and 71.13 is 185.38. Hence the design shear at the center of the span is taken as 185.38. The required capacity of the shear reinforcement at any section of the beam would be VUS is equal to VU minus VC. Now VU we obtain it as 185.38 and VC is the capacity of the section. Now we have obtained that already here. VC was 102.9. So what you get VUS is 82.48 kilonewton. Now referring to clause 40.4 of IS 456, we get the required spacing of two-legged 8 mm 5 stirrup as 145 mm. For that you need to consult clause 40.4 of IS 456. That gives us this formula. VUS is 0.87. Sorry, this is not 145, it's 117 here. So we are correcting it here. It's 117 mm. So VUS is 0.87 FY ASV into D divided by SV. ASV, so what we get is 117. FY we know it's 415. D is 532. ASV is the area of the stirrup, the legs of the stirrup, two legs, so it will be the addition of two legs of the stirrup. SV is what we need to obtain, is the spacing. So it's not VUS that we are actually obtaining. Again, there is a correction here. So it's the SV that we are obtaining. So in this you have SV here. This is SV and this is VUS. Okay. As per clause 6.3.5 of IS 13920, the spacing of the stirrups in the mid span shall not exceed D by 2, that is 532 by 2. That's not the case here, it's only 117. So what we are going to provide before providing that, the spacing of the links over the length 2D at either end of the beam as per clause 6.3.5 of IS 13920 shall be least of D by 4, that's 532 by 4, which is 133. 8 times the diameter of smallest bar, that's 8 into 16, it's 128. However, it need not be less than 100 mm. Hence, what we are providing is two legs 8 mm 5 stirrup at 115 mm center to center at left, at right end, over a length of 2D, which is this much, 1064. But even for the center portion, we need to provide the same. So we can go on for whole of the beam. We can provide 8 mm die stirrups at the rate of 115 mm center to center throughout for 5 meters of length of the beam. So in this lecture, what we have done is that we have designed a beam for flexural forces as well as for shear forces. So we have detailed the beam as per IS 13920 for ductile detailing and for strength design from IS 456, such that we have provided the longitudinal bars as well as the spacing of the transverse reinforcement, taking into account the special confining zone at the ends as well, although there is no difference here in between in the central portion as well. Thank you.